Hello, ladies and gentlemen. This is Alice. I'm so glad to meet you on iCANX talks today. Yeah, warm greeting from Peking University. This month we start our talks from Professor Markus from Max Planck Institute. And next week we'll have a demon is from University of Limerick. Yeah, last 2 week of this month, we will have the Light Rising Stars, the final defense. So this will be, big month for all these kind of new things come on. Today our talk, our super speaker is Professor Markus. Yeah, his topic is quite interesting. It's about the nanotechnologies used for the soil, how to make the carbon neutral. Yeah, so we have a big panel today. Everyone sees that almost the key players of iCANX was here. So because today we also have something to announce, for a big announcement for next year's, iCANX Davos Summit. So let me first introduce Professor Markus and Antonity. Yeah. So Professor Markus was, a director for Max Planck Institute of Colloids and Interface for 30 years. Yeah, he's a super, scientist, was very famous, on the polymer self organization and the interplay of organic and inorganic materials in terms of neutral control and the polar material, artificial, photosynthesis and materials for energy storage and energy conversion. And in the last years on biosourced materials and carbon negative materials. And I also have a very colorful life, he like, gardening, preparing fusion cousins and plays in the rock band. Yes, yeah, Markus, yeah, Professor Markus, yeah, without further ado, please, yeah, so the stage is yours. Share your slides, please. Okay, here comes.
Okay, you see everything? So first,
Yes.
of course, thank you for inviting me. It's a big pleasure to be along this very young, very international format. Yeah, and this is also why I choose something which is maybe not what you expect, because of course I do also serious research, but in this case, indeed, I want to show something which I think will excite many people from very different countries, because it's about, of course, carbon neutrality and what material science can contribute to it. Yeah, I think this curve is famous, and this is what it's all about. Yeah, and you see, this is the rising curve of the CO2 level, and we could plot sea levels, catastrophic events. So many things are related. And I think it's a little pressing because this is essentially an exponential curve. Yeah. Is something happening? And again, mankind in 2019, when this curve ends, made one of the biggest experiments. It's called Corona. And in Corona times, no one was traveling. In Beijing, the sky was blue because industry was put down. Cruise ships were not driving. And so if this would work, we should have seen it the last 4 years. Yeah, and you see here, the average increase in the last years is 2.86 ppm per year. And if you go to the new data, these are new hack data, it even has increased. So be aware that staying at home does not help at all. And there are colleagues from social science who say this is an expression of mankind to strive for higher wealth, higher education, and all that comes with energy. So there's nothing you can easily change with the curve. So where did all the energy go to if it did not go to cars? One answer is definitely the internet, because it's well known that the data infrastructure, so what we do now, in fact, mobile phones, yeah, is one of the biggest sources of CO2. And within the same level, we save energy, we pump out artificial intelligence, we pump up indeed our networking activities. So sitting at home, not traveling, and doing super massive parallel computer games or also science, you see, will just move the CO2 generation from one corner to the other. Yeah, so maybe there is nothing you can do like that. Yeah, because giving up communication, giving up mobile phones, giving up everything, I think man will not do that. Yeah. Bitcoin harvesting, one of the most stupid things you see, this is terawatt hours only to make Bitcoins. Yeah. And if you go through the numbers, yeah, and you see, for instance, Bangladesh or Switzerland, yeah, Bitcoin mining is meanwhile the fourth of all energy sources directly behind. And we can really discuss if this is needed or not. Yeah. So, but this is how man can be. Can we do something? And I think this is what most people think. Yeah, they drink a box of beer. Yeah, they do protests and they think the end is near. But you know, science is not like that. And science is always looking for a solution. And that is what is my talk about. If we check, for instance, world oil production, it's 4 metric cubic kilometers. This is enormous. It's 1K times 1K times 4K. So it's a big, big, big pile of oil. But if you compare it, for instance, with plant growth, yeah, you see indeed the plant growth is 30 times the amount of oil production. Yeah, and plant growth obviously consumes CO2. Yeah, and I tell you that about 7% of biomass is sufficient to compensate for all the negatives of crude oil. Yeah, and as at the moment, 11% of biomass are already part of farming cycles where we throw away 10% of that. Yeah, obviously we only have to deal our plant waste better, collected plant waste better to get a deep, 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 deep sink. Just for a side calculation, and this is very exciting because it gives hope. Yeah, every year nature binds 60 gigatons of carbon from the atmosphere. And if you compare it to the CO2 contained in the atmosphere, it's 30 ppm per year, 28.6 ppm per year. So you see, indeed, you could take that as the theoretical recovery rate of the atmosphere. Every year we lose 28 ppm. Yeah, but of course, nature is in equilibrium. It's also regenerated. Yeah, so we have to find, so to say, a way to break the natural cycle. Yeah, and this recovery rate you already see here in this curve. What you see is summer-winter cycle. So obviously, when the plants are growing on the north half hemisphere, the CO2 is rapidly turning down. Whereas, of course, if it's getting fall and the leaves are decomposing, the CO2 is coming back. Yeah, so take the leaves and do something with it, and you see nature could heal the planet by itself or by herself. This is, I would say, all mathematics. This is the analysis of an elder man. Yeah. So how to do that? Yeah, because in the very end, we know biomass is collected CO2, the nature is in equilibrium. So we have to find now the way how nature is really circulating biomass and where, so to say, are the side streams. And I like this question because we are talking now about a gigastar. Gigastar here is not superstar. It means a gigaton material star. And I ask usually my students the question, what is the most abundant polymer material on Earth? Yeah, and the most important one. And up to now, I never got the right answer for it. Yeah, because indeed, if you take polyethylene or polypropylene, it's 200 megatons per year. We just learned that cellulose is about 60 gigatons per year. But the stuff you don't see, the nanomaterials, are so-called humins. This is the black stuff in soil. Soil is black because it contains nanocarbon compounds, and the content of these humins on Earth is 1,500 gigatons. So you see, the most which is on planet we don't see, we don't consider because it's below our feet. I made a homemade, very bad drawing of that. Yeah. So you see the typical numbers, and you could focus, for instance, on the atmosphere. These are 870 gigatons of carbon. Land biomass is only 550 gigatons. Yeah. So even growing forests and burning forests is changing the numbers, but not in the way as we want. Yeah. And if you go to soil only, and soil is defined as the top 20 to 30%, which you can touch easily with a shovel. Yeah, you see it's 1,500 gigatons. So a little change of this number would immediately change the atmospheric concentration, and all is nearby and close to our hands. This is the philosophy. It's not my philosophy, I have to say, because this is found out by many people many times. You see a typical soil horizon in this picture. Yeah. So here in the top layers, you see the carbon species I'm talking about. Yeah. And already in the Paris Climate Convention, the so-called 4 per 1,000 initiative was founded, which said add a little carbon to soil and the planet is carbon neutral. And it's done by those people who have the least income. It's done by the farmers. So this question is true sustainable in the sense of the UNESCO, because it's socially sustainable and it's chemically sustainable. This is the idea. It comes to the right time. This is another international world organization. It's the World Agricultural Organization, and they're defining the quality decline of soil. So our farming soils are getting worse and worse and worse and worse, and they have to heal. And you just have to focus on the red spots, and you see indeed China is one of the countries which is in a very worse situation, because their type of agriculture is declining soils with soil quality with terrible speed. Similar things are only seen in small parts of the Amazonas basin. Yeah, it's seen in some parts of Africa. Yeah, I have to say, indeed, many of these countries, farming is coming now from China, so they're using the bad practices. You see Ukraine and Russia, the war situation also there, the soils are declining, and very high severity means indeed we don't have food in 30 years. So if indeed this type of atmospheric technology would improve the soil quality, we would have, so to say, two birds with one stone. And again, all these data are public, you can just check, but we prefer not to know them because we have enough problems, and then it's typically mankind not to look where you have to look. The two questions are related, and this is a statement by the US Department of Agriculture. Yeah, and they say, general, from a non-really scientific, from a farming perspective, the best quantification of soil fertility is the carbon content. And I love this statement because it gives, in the very end, power to material science. We are doing carbon, we can control functionality of carbon, and if we can really improve the carbon content with the right carbon, soil fertility is in our hand. I don't have to learn too much biology. I just learn carbon making and I have the chance to improve fertility. This is now metadata, it's our own metadata. So after this statement, of course, I went into libraries, we did own measurements, and this is practically, the orange samples are our samples, soil samples collected in Brandenburg. Brandenburg is the name of my province. Yeah, and you see the carbon content in soil, it goes logarithmically down below, 0.1%, 1%, 10%, and 100%, of course, is no soil. So the strangest soil in about 30% of carbon. This is peat. Yeah. And you see, if you count now on the y-axis, the number of microorganisms, which is in the very end, the happiness of biology with the soil, you see it's a linear relation in log-log. It's incredible. It goes over no less than 8 decades. Yeah. And this really means US Agricultural Organization was correct with the carbon content. I control microbiology in a rather strict sense. At the moment, we cannot understand that, of course. Why should carbon be related to fertility? But I will explain you that later. I will also explain you the real riddle on this level, which is that the number of organisms goes about with a third exponent of the carbon content. So if you double the carbon content, you get 8-fold the fertility. Yeah, this is the point. So something very strange is hidden in this universal law, in this meta law. Yeah, we have to find it out as a scientist. As I said, it was invented a number of times, and I always show these pictures. I showed 2 of them overall to give some modesty, because all these things were done hundreds, thousands of years ago by very simple people without high-end chemistry, without nano knowledge on carbon. Yeah? So these guys are the so-called Terra Preta Indians. This is South America. You don't see it. It's the Amazonas basin. And about 500 years, all these people died because the Spanish brought the measles, another of these pandemia, changing the world. Yeah. And if you go there nowadays, after 500 years, you still find the soil full of black soil. So the thing you see, this is black, artificial black soil, anthropogenic black soil. If after 500 years you plant corn or maize on it, you see it grows. The soil is fertile. And the fact that it's good for 500 years means it's sustainable. Whereas ordinary jungle soils, this is what you do if you take away the jungle, is a fallow soil, it's a white soil. And if you grow indeed corn or maize without the fertilizer there, it does not grow. So this is just the proof that Indo-organic tribes already knew it and we forgot it. You can even do archaeology and you find out how they did it. They did not do the carbon by fire. They did it under earth in something you could call a clay double bubble reactor. Yeah. So obviously you have to exclude oxygen from the carbonization because you want to have a high carbon yield. So no CO2, no CO, as minimal as possible, I should say. Yeah. And they did by developing these funny looking mans. And you see, for instance, if you go to left bottom line, the head is mobile. There you put the biomass in, and then it's a seal, an overpressure valve to keep the oxygen out. It's not flame carbonization. No way that this is flame carbonization. And this brings me indeed what we did. We did hydrothermal carbonization. And hydrothermal carbonization, we assumed that this is what was done by the Indo-organic tribes. The temperature you can have in such a reactor is maybe 120, 130 degrees. But it's enough to do carbon in 4 weeks. We do it a little higher at around 200 and we do it in 90 minutes. So this is just an acceleration. Yeah. It was described in Science by Friedrich Bergius, a German. And the problem is all these papers were in German. So most people cannot know because those days language was still a monopoly. I just show you a picture. So it's a chemistry simple because from a carbohydrate, you make carbon and hydrate, which is water and carbon. So the product is just water splitting. You take out water from the biomass and you end up with carbon. Practically all the carbon stays like that in, but also the nitrogen and the phosphorus stays in. Yeah, it's incredibly cheap. And if you do it the right way, the structures are incredibly well organized. So this is now really nanoscience. You have monodispersed particles, you have rods, you have nanosponges, high surface area, yeah, exchange catalyst, and already with a sponge, you might have an idea why this is good for soil because it will, of course, bind water, it will bind nutrients, and it gives housing to the microbes, which then live in the pores. So all that obviously is already explained from the sheer picture. We did it in Germany about 10 years ago, and we built a machine. Yeah, this is the machine, and again, you see it's a pilot plant, but lower left picture, you see our flasks or containers are now 800-liter containers. So this is rather big science. Yeah, this machine, the feed upper left side is a big mouth, and you can use indeed a machine to put in the biomass in. So you see this machine is built for 5,000 tons per year, because if I want to save the planet, it has to be simple and cheap. And such a machine in principle has to be able to construct it in Africa, in South America, also by people who don't have a lot of money, yeah, to pay for noble steel and so on. I think the most impressive thing is the video. What you see now is the synthesis of carbon with 1 kilogram per second. This is 5,000 tons a year. And I just give you a video. It's water, so usually the hole in the container is sealed. Yeah, it's not toxic, but we prefer, of course, to follow safety. So the non-sealed thing is only done. To show you the 1 kilogram per second. Yeah, it's water and it's carbon, and this is the product I'm talking about. Those days, it was good for soil, but it was erratic. So I will not pretend that you can know everything, and sometimes you have to wait for 10 years to learn the trick. Yeah, and we did not understand why some of these samples were very good, some of the people were less good. And in the very end, it turned out it was not the carbon, it was a few molecules adhered to the carbon, which were doing the job. And again, this is a fantastic story because people again found out before. Yeah. So what you see here in the upper left picture, this is the island of Orkney. It's in the north of Scotland. Yeah. You see a beautiful beach and then you see a meadow. And I tell you, there are no meadows at Orkney except man-made Orkney. So this meadow is around 6,000 years old. 8,000 years old. So this is one of the oldest you see here. It's very fertile and it's stable now for 8,000 years. So once the carbon is in, nature keeps it, and nature prefers to have fertility. What is the secret of this stuff? Why it's so fertile? And the secret of this stuff, how the people did, again, this is early Bronze Age. Yeah, so this is far from technology, but they had two things on the waterline. One is kelp, which is an algae, and the other is calcium carbonate from seashells. They mixed the two, and under these base conditions, indeed, carbon formation takes another part, which is called humification. Where we don't carbonize, we humify now. This is hydrothermal humification we do, and because of that, of course, it's much better for the soil. Here I have to point to young people who are doing the job. This is Professor Van Yang from the Northeastern Agricultural University of Harbin. She is in her 30s, but she is now boss of a big state lab in China doing exactly these molecules. This is a typical humic acid molecule, how it looks according to the techniques we work. So we don't do particles anymore, we do polymers. A typical humic polymer has a molecular weight of 5 to 20,000. Yeah, so, and because it's a molecule, it's much more active. If it goes to a particle, it can make a monomolecular layer of this polymer. It doesn't need to be a big particle of the micrometer size, so you get everything already with a 5 nanometer layer. This is coating of particles with entities. And to tell it from the beginning, this polymer is a wonder, and it's much better than the most synthetic polymers, and it's natural. Yeah, it's highly surface active, and you might guess it because you have carboxylate, aromatic groups. This looks like a big surfactant. It's a pH buffer because it's called carboxylates and phenolates. Yeah, and you have about 1 acid group per 1,000 mass units, which makes it a rather good solid state buffer. It's a redox buffer. So you can store about 0.5 moles of electron per kilogram of this material. And in spite of the simplicity, I have to tell you that the lithium-ion battery is only 6 times better. So soil, in fact, is the biggest battery on Earth, and the materials has an efficiency to store electrons, which is 16% of the one of a modern lithium battery. Yeah. And in addition, of course, it does water binding, it does oil binding. So all that is in this funny structure, which you create from the condensation of biomass. It's breathtaking, and it's nature. Yeah? Because nature, a long time ago, made this polymer and everything we see around. It is believed that the oldest humic acid reservoirs are 2 billion years old. So it's older than plants and older than animals. Yeah? And again, everything else developed in the presence of this molecule, and this is why nature goes so well with this molecule. So it was first a molecule, if you talk about now genesis, yeah, and then biology developed in the presence of the molecule. Big words. We can do a lot of analytics, and you see this is what you do, of course, if you have an institute. It's a lot of aromatic carbons. Please look at A. It's, so to say, full of different functionalities of aromatic carbon. This is, by the way, where the electrons are stored. We have carboxylates, which is in the higher range. Yeah, we have aliphatic carbon. So there's a rather high amount of aliphatic carbons in the structure, which is in the very end coming from the lipids and the former cell membranes of biomass. But this is contained and kept contained into humic acids. Then there is, of course, C, for instance. This is pyrolysis MS. So this is decomposing the molecule, and we see all the little structures inside. And from the fragments, let's go immediately to D. Yeah, you see indeed what natural and humic acid and artificial humic acid is composed. They're very similar. We can, of course, fake natural humic acid, but what you see is one of our top candidates. And you can attribute about a fifth of the component to protein fragments, to polysaccharide fragments, to lignin fragments, aromatics of other type, non-lignin type aromatics, and lipids. And all of them contribute about equal to the structure if you take indeed a good artificial humic acid. So there is a science on it. It's solid state characterizations. We do, of course, all the advanced things, so we know our humic acid quite well. This is the real thing. So we are living in Brandenburg, as I told you, and Brandenburg is not a fortunate province because we only have sand. 800 meters of sand, and in sand, of course, nothing grows really because water is not retained. Yeah. In the picture, you see indeed sandy soil and artificial soil, and the artificial soil is conjugated. Conjugation is a principle we know from biomedical polymers. We add the humic acid, and the humic acid binds to the surface of the particles. And if you now do SEM and see, instead of seeing plain crystalline particles, you will see rough surfaces full of pores, so high values, low values. And this is where water is bound, and this is where indeed minerals are contained. So this is where the real action of soil is happening. So fertile soil is a support of minerals with a, so to say, surface texture of organic material where you can put the life onto. This is the scenario of life, what you see with SEM. This is a classical experiment for simple farming experiments. You have sandy soil, and then you put nutrient, it's NPK, it's a fertilizer, and you see the weakness of sandy soil is that practically no nitrogen is kept back, no potassium is kept back. You fertilize, but it just goes down the drinking water. Phosphate you can bind a little better, yeah, because phosphate, of course, is more interactive to minerals, but all of them, typically 90% of your fertilizer is wasted when you fertilize sandy soil. This is why no one is fertilizing sandy soil. It's a waste of money. This sandy soil now is turned into artificial soil, and you see nitrogen binding is 10 times improved. Potassium binding is 8 times improved. Yeah. And even if you mix sandy and artificial soil, about 20% of the fertilizer is kept in the sand. This is a very good value because in cultivated soil, yeah, which means used up soil, this soil in the previous diagrams, which was red and orange, yeah, 90% of the fertilizer is wasted. So you see, indeed, with artificial soil, we can create better fertilizer bending. I should give you also the example of black soil. So this is a good black soil from China. And you see here, nitrogen and phosphate is perfectly stored. Only potassium is flushed away because even this top black soil has a certain off balance of ingredients making the perfect, theoretically perfect humic acid. So this is now data from NAU, from the big lab in China. What you see are indeed seedlings, corn seedlings, Yeah. And the only point important is that the control group, which is fertilized, is not the best. Yeah. That we can do much better with so to say, non-fertilized samples with humic acid. So adding humic acid indeed makes the physical chemistry of soil better. And these little seedlings are very happy about it. Much too much data, yeah? Now you measure everything: stem diameter, live width, plant height, their phosphor content, nitrogen content. And the only thing important in this diagram is the reference group is pink, and our best group, optimized group, is blue. And indeed, containing protein content, containing phosphor content. Overall, the nutrition power of this food is 20% better than the best farming practice currently available. We usually have on average up to 20% improvements of the farming productivity. This just, of course, resonates on the primary statement that the best measure for soil fertility is carbon content. We start now to understand what type of carbon it is, because there are also yellow groups and blue groups. So by gambling around with the humic acid or the biomass you make the humic acid from, you see what is good and what is bad. This is the real scary thing. Yeah, and here you can believe in wonders. This is why this slide is called the wonder of humic acid, which is the biological. So our primary soil, the table, is well characterized and it contains 2.8 weight% of carbon. And again, remember, please, we want to store carbon into the soil and create fertility at the same time. We want to solve two problems with one stone. We add about 0.3 per mil. So 2.88, we add 0.03 to it. And usually you should not see the difference. But if you go into the data and measure the so-called TOC, total organic compound, after 1 month, you see that the soil contains 5% of carbon. And then you make spectroscopy. These are the pictures A, B down below. You see it's the 5% are all humic matter. So how can I add 0.3 per mil and get 2% added? And this is, well, wonders, we have two answers. One is religion for wonder, and the other answer is biology. And indeed, in this case, it's biology. It's that the humic acid is activating microbial photosynthesis. Maybe known by many of you, the real photosynthetic players on the planet are not trees or grass. Yeah, indeed, bacteria are much more efficient. We have cyanobacteria, rhodobacteria. So there are many bacteria which can eat CO2 and turn it into metabolites by photosynthesis. And these photosynthetic pathways, the old pathways of photosynthesis, are about 30 times more effective than the photosynthesis in plants. Bacteria, their only strategy is grow. They have to outgrow everything. A plant can be tall, can defend itself. There, indeed, mass increase is just one of the many parameters a tree has to fulfill. But if we want to bind carbons, of course, microbes in soil are ideal candidate. And as that, indeed, if you take these numbers and you calculate them on hectare, we add 1 ton of carbon and we harvest 70 tons of carbons by something you could call microbe farming. Microbe farming is only possible with added humic acid. And this, of course, is where all the high numbers really come from. Again, same diagram. What you do now is you do something which is called metagenomics or metagenetic experiments. You take the top sample A and then you start to analyze what type of guys are in. Yeah, and in this case, indeed, it turned out to be a very, very old universalist. So this guy is 2.8 billion years old, Cupriavidus necator. Yeah, and it's a guy who can do everything, but also very effectively photosynthesis. It's also say the pioneer microbe, or one of the pioneer microbes, which made the planet Earth habitable. So these guys changed the face of the planet and created the oxygen atmosphere. It was not done by plants, it was done by guys like that. Yeah? And this is indeed the thing we refined, which means the biology of soil is super old. And below your field, there's not only a lot of carbon, there are also very old guys doing a lot of work. This is how it looks, and it's more the impression of science, the art of science, that I can really go through the numbers. Yeah, so people are analyzing, this is done by a company, all species at the same time. We find up to 3,000 different microbes, which we align according to this color code, yeah, to different O2 numbers. In the very end, you get an idea how indeed the microbes are related. And this flower on top, B, is indeed things when you add something which you see and other things which you don't see. So we can really follow the addition of our chemical compound by the change of the population of the microbes and make a molecular model on how the microbes really interact and how they react to our optimized humic acid. It's in a hand now. We don't have to take one humic acid. We can make humic acid. We can make them differently. And with this tool, of course, we can, well, maybe solve the riddles of system microbiology. I like this one very much because one is Geosphere or Biosphere 2. It is an experiment of the University of Arizona, and it was meant in the preparation of a moon settlement or a Mars settlement. So indeed, a number of scientists, around 100, had the chance to create a little house, yeah, to put everything in they want, but then they had to keep an equilibrium inside to survive. Yeah, so indeed they had fish ponds, and you see trees inside. Then the door was closed, and the sad thing is this experiment had to be stopped after a few months, because in the very end the system was running out of balance. Yeah, the system contained not too little oxygen, it contained much too little CO2, and because of the much too little CO2, the system, so to say, the biology had to react. Plants could not grow anymore. CO2 is food for the plants. So obviously something was absolutely not understood, yeah, in this type of system biology. This is my personal biosphere. It's a tube, glass tube, and it's sealed on top and the bottom. We put in some water, and then everything is in equilibrium except that we add light. And what you see is indeed green guys, red guys, black guys. All the microbes start to settle the soil to a depth of up to 40 centimeters, and all of them doing something different. So indeed, the black spots, they're binding nitrogen from the air. Yeah, they are anaerobic. Yeah, the green spots obviously do CO2 fixation. So indeed, CO2 generation by metabolization, like in the black spots, and CO2 binding. The tube is closed, remember, yeah, is in equilibrium. And this tube is 3 months old. It survives in equilibrium, and it creates patterns. So this is automatically pattern formation. And this is most easy to understand, but because the black spot is anaerobic, so it doesn't like oxygen, and the green spots generate oxygen. So obviously they have to live side by side, but they cannot live on the same spot. And here you understand why the battery function of humic acid is important. Yeah, indeed, here we have a redox gradient. And this redox gradient has to be stabilized, and the stabilization agent is humic acid. No humic acid, no redox gradient, no co-cultivation of different species supporting each other at the same time. This is the secret of the third exponent of the concentration. A third exponent of the concentration is a linear distance. It's, so to say, change of redox per centimeter. So we can prove with the about third exponent that indeed that we can stabilize higher gradients. So redox difference divided by distance, the distance is smaller, and this can only be when indeed humic acid stabilizes these gradients. A little about marketing and the future. We love to live in cities, but we love to live in nature. And this is why architects all over the world have visions of the architecture of the future. And the upper left picture, this is not a vision, it's in Milano, so in Italy. And this is the so-called Bosco Verticale. It's the vertical forest in English. Yeah. And these houses are super popular. These flats are unpayable, and only rich influencers and show stars have the money to live in these houses. So obviously, the experiment was successful. The picture on the side, this is what is currently built near Singapore. This is the forest city in Malaysia, so near Singapore. And you see it's the same idea. The original idea of these green walls was, of course, water evaporation and air conditioning. So you have a better city climate, a much better city climate, and of course, higher oxygen content, impurities are filtered out. But beside, of course, you also have this system microbiology, carbon binding, and so on, which the architects do not know, I have to say. So this is science, yeah. But you see, obviously, this is the way to do. And believe me, you need a lot of artificial soil for that. So I'm sure that my little factories will not run out of demand, because even if you add only 0.3 per mil, you need a lot of tons for such a skyscraper. Going to the future, yeah, this is indeed Shenzhen. Yeah, this is a fantastic French architect, Vincent Colloids. I can only recommend to check for his work. It's urban farming. So every farmer is having one of these bubbles, yeah, and they're piling these bubbles on top. And it's more than only art, because this is constructed, calculated. This indeed makes sense. You can hybridize it with living apartments. This is no problem. But maybe this is the way we might live in the future, just because of climate conditions and similar things, but also, of course, for carbon binding. And this is indeed a design of a super skyscraper, so to say, Geosphere 5, by an Ukrainian team. It has won the competition for design. And it's just funny because, of course, I love science fiction, and to have a reasonable concept how the future might look like is always enlightening to me. I am at the end of my talk, to leave enough space, so 45 minutes. Yeah, I wanted to give you some conclusions. Yeah, you see, biomass can be the source of carbon materials. This is why carbon materials in general, also in energy storage, also in photocatalysis, have a fantastic future. I think we're entering an age of carbon, which includes graphene and nanotubes, of course, but there's so much more in carbon materials, and all of them can be made everywhere from biomass without fossil resources. It's in the very end a very sustainable but also democratic material. I was introducing the concept of carbon negativity. It's not only to avoid carbon emission. We have to find processes where carbon is first bound, CO2 is first bound, and plants are doing that. Remember, please, the 30 ppm binding capacity. We really don't need big physical machines as long as we throw away leaves and let biomass rot. 30 ppm is collected, and taking these side products and making something more stable carbon out of it is carbon negative. So we subtract indeed from the atmospheric system. Yeah, my most beloved candidate, and it's a personal preference, yeah, is synthetic humic acid, because this allows anthropogenic soil management. So we get an understanding of the complex processes in soil, which is much more, and all are promoted by something you call a redox mediator, and which is indeed a carbon compound. In the very end, it allows terraforming. Terraforming is not only on Mars, as Elon Musk will tell us. Terraforming is also the green wall in Africa, the Great Green Wall in China, billions of trees to be planted, but the trees will not survive without humic acid and without this type of artificial compost. Yeah, it's has the clear potential to be effective on the global scale, and this is now not restricted by science, it's restricted by politics. Yeah, as long as we prefer not to change things, we will not save the planet. And this is the real thing. So I fear science has to have also a political voice, because otherwise it will not happen. I told you about polymers for microbiome management. It's a new concept. It works also, by the way, in white biotechnology. We can make also the guys living in stir tanks much more happy by providing the molecules which help them to survive. It's a general truth, yeah. And other biomicrobial communities mostly means indeed, for instance, what we have inside of us in our intestine. Yeah, also that is exactly such a microbial community. So maybe humic acids, biomass products also have a health perspective. Let's see my last slide. It's a simple sentence. Yeah. What is saving the planet? And this goes a little with Siddhartha Buddha. Yeah. We have an offset absolute of 9 gigatons per year. And it sounds like a horrible number. And this is why many people are getting depressed. But we have 8 gigahumans world population. Everywhere people are living and can help. It's not restricted to industrial countries. And we have 7 gigahectares of used land, which is indeed farm, pasture land, forest land. And allow me the simplification to divide away the gigas and tell, if we can handle 1 ton per year and per person and per hectare of land, yeah, the world is cured. Only 1 ton per person. And this is, I feel like that, what I do in a week in my garden when the grass is growing and I fill my compost. So this number is not unusual. We were talking, by the way, about 70 tons per hectare in some of the experiments, so we don't have to do it everywhere. And this is the message. Thank you very much. You see, high-end nanoscience applied on very simple questions.
Okay, great. We got your message. Yeah, to 1 ton a person, per year, that's possibly, yeah, reasonable for everyone to jump in. So let me introduce our, panelists today. Yeah. So thanks, Professor Markus, your wonderful talk gave us a lot of thinking about, this technology, also for the social, responsibility for everyone. Yeah. So today we have a super panel. First we have a panelist, Martin Suhr, professor at North Carolina State University. He don't need further, instruction, because he showed up on the stage, be the moderator of iCANX many times. He's a moderator for many talks. So welcome, Martin. Also a super, nanoscientist, did a lot of work. And we have Paul Weiss. Yeah, it's your old friend, Professor Markus. Yeah, Paul is in a Golden Conference. We will come in a little bit later. Yeah, so Paul is also, moderator on iCANX for many years. Yeah, actually, is a co-founder of all this kind of, platform. So Paul, welcome. And we have Min Yue. So Min Yue is a professor in Switzerland, in Lausanne. So yeah, welcome Min Yue. Min Yue is not in the technical part. Is also she is a super expert for the economy. So today I think Min Yue will have some questions for this words, for the carbon neutral, how to deal with this problem. So let's welcome everyone to jump in the panel. Yeah. So Martin, maybe you come first for the questions. Martin, please.
Yeah, sure. Yeah, sure, definitely. Mark has an extremely interesting talk, and I think from a materials point of view, it's very nice to get that challenge. But sometimes we think polymers are the enemies of the environment, but I like your message that polymers are the cure for the problem. So I had a question related to the carbonization and soil health. Given that soil has a lot of metal ions, is the carbon playing a different role than just being a water retainer or helping with a microorganism, is it actually helping hold on to some of the nutrients that get washed down? In the picture you showed where you're comparing two soils, the black soils and the washed out soil where the plants are not growing, you can actually clearly see that the color is telling us that there's depletion of metal ions from where the roots are going to be growing. Is the carbon actually helping trap those essential metal components to change the total microenvironment?
Thank you very much. It's an absolutely brilliant question, and you're really a careful observer, because we don't need complicated experiments. Already looking at a simple soil horizon tells us many of the ongoing processes. And again, this simplicity is, of course, the art of the true master. Yeah. Yes, you're absolutely right. There's an interaction, of course, with all minerals. We have phenols, we have carboxylates, and again, we are relying on micronutrients. And we made some experiments along that, but again, this is a very, very big field, and I have not enough students to ever do that. But indeed, iron, of course, is bound in these siderophore-like structures. So iron will bind to phenols, and we need iron support. Yeah. And this will be very important, for instance, for food polymers, because iron supply is the biggest problem of vegetarian people. Yeah, and indeed, having something stimulating iron uptake, both for plants and for people, of course, is an open question, which I think can be solved with similar polymers. The other thing, of course, we need is manganese. All the structures are very good and bound to carboxylates. So we are very sure that it is activated. The most crazy thing we observed, still to be understood, is phosphate. Because if you applied a phosphate fertilizer, it's an old problem that 90% of this fertilizer is mineralizing, means it turns into an insoluble phosphate, iron phosphate, for instance, and is useless in the soil. If you add humic acid, this iron phosphate is broken up again. Yeah, because it's turned in variant from iron 3 into iron 2. You can measure that, and the plant can start to eat the iron phosphate. So not by ordinary dissolution, but by redox-activated dissolution. And these fantastic stories, there are many in the game, but as you see, we are doing that now for 3 to 5 years, and many of these riddles, the questions are asked partly. You made it in a very well way, but we are not there that I could really ask all the mysteries. Yeah, but yes, interaction with iron, with all the minerals is important, and be aware, of course, that plants need to chew also the minerals, because otherwise they cannot build up their metabolic functions.
Okay. Yeah, actually, in your comment, you kind of hinted to what I wanted to follow on next, because sometimes as chemists, as material scientists, we make these very beautiful structures in our lab, like the way you showed with your humus, the human molecules, with all the carboxylates very well positioned. And I noticed that you have a 1,2 dicarboxylic acid, and you also have 1,2 phenolic components in your structure. So I was looking at those, and I would say, okay, if I expose these to a soil, do I then expect that if I move from the molecular level, the structure, the mesoscale, the one micrometer to about 5 micrometer, the morphology of that polymer is not going to be the same as we study in the lab? Because in the lab, we may equilibrate the structures a certain way. And the reason that question is coming to mind is tied to what you showed at the beginning when you're making the carbon. You can make all these different types of carbon. And I'm actually in that world. I also make a lot of carbon materials, but at the macro level. And what we have seen is once you get to certain sizes, the rheological behavior of any granular system that you build is extremely different, right? And if I put these polymers in the soil and they are chelating or they're getting deprotonated and they adopt a different morphology, then what is the net change in the rheology, the flow behavior of the soil, and does that affect actually the plant growth? I don't know. I'm just
no,
curious.
brilliant. Again, here I have to point, humic acid research is maybe 100 years old, yeah?
Yep.
And again, it starts with molecules, and to get the molecules, we have to apply very high acid or base conditions. This is the way how humic acids are isolated. But if you give back the ions, immediately secondary interactions set in again, and you get something which is called the humin mineral complex. It's just a name for something you're describing, and it's full of rheological phenomena. First, it's gelling, which you need to bind the water, because water in the gelled way, of course, is much more difficult to remove than in the, so this gelling is important. Secondly, what we all know, if you go after the rain into the forest, you have an elasticity of soil. And this elasticity of soil is exactly the structure you decide. So many things we can observe are in, sad to say, I'm not a rheologist, yeah, but you're right. The real structure is not a molecule of 3 nanometer anymore. It's a very complex superstructure on all hierarchy levels, and it ends maybe in the micrometer range, yeah. So there's a whole set of self-organization processes, maybe not of the most beautiful organization type, yeah, periodic or so, yeah. But it's set in, and you see that the properties, this gelling, the water binding, it's mostly driven indeed by secondary reversible interactions, which is, of course, metal ligating.
Very good. Maybe one last question. This is coming from me growing up in an African village and having to use hand tools to farm. I can tell you, when I am working on my father's land, which was mostly very washed up soil in central Kenya, and then going to the Rift Valley, which is very heavy in agriculture, where they had the black soil. I loved working on my grandmother's land than I liked to work on my father's land, because our land was hard, right? Again, coming back to that washing, when you wash out that carbon and you lose that black texture, you realize that cultivating that land is not so much fun. It's not, it doesn't have an easy flow, right?
Sure.
And I wonder whether part of our agriculture is because we have lost touch with the land. We don't feel it. We sit in a big tractor somewhere and pull a plow, pushing buttons when we're very distant, so in an air-conditioned cabin, and just assuming the soil is an entity. While the person who is doing the organic farming, most of the small-scale farmers, most of the people you showed in the traditional Amazonian communities, they till the land by hand. They can feel it. Are we losing something as humanity by getting over mechanized? Is there space for us to go back and get in touch with the ground so that we can understand the damage we're doing?
Wow, what a vision. What you say is what I observe even with my own farmers. Any gardener, any lady putting peat to the roses is doing exactly that. If you are working in your garden, even if you are a professor, yeah, you really get a reconnection to nature. And I think it's a luxury behavior, yeah, because not everyone can have a garden. Yeah, that's the point. But this rebounding to earth is giving me, but also simple people, farmers on the countryside, deepest pleasure and a wisdom we partly don't have anymore. I agree. Yeah. And if I want to learn something about soil, I don't go to scientists. I go to those guys and tell them what I've observed, and they're able to discuss with me and help me with my problems. Yeah.
So there's also room then for a social scientist in and engineer nanomaterials then. They might have to guide us to where
today,
to look.
Today we have a social scientist here, so yeah, Mingyue is major for the social science. Yeah, so actually, yeah, Mingyue, you mute. Yeah, so okay, did you have questions or comments?
Thanks, Alice, and thanks, Markus. Actually, it's first time I really learned a lot from this topic. You can see from my background, so I live in Switzerland, you see the Lake of Geneva and also the mountain area. So I should say Swiss farmers really care about the environment. It's not just like the recent years. I remember I was involved in the vote to, how to say, avoid using any kind of toxic pesticides. But normally they care about this part of the soil quality. So actually, it's the first time I learned soil material can be also contribute to the carbon neutral and a carbon zero, which is actually is a very important task today. So my point, I think from economic perspective, it's a long-standing debate. Every time when we talk about this ESG, environmental social responsibility, always we talk about, okay, how much it costs and when we got some benefit. So I have two questions actually address. The first point is regarding the trade-off between this cost and maybe some economic outcome. So at least from my understanding, soil material is not so much costly, but the process, I think the what you just introduced is maybe costly. So did you have any kind of thoughts about this balance or some trade-off or some planning for the economic cost and outcome? So this is my first point. And the second actually is also relevant. How about the timing issue? So when we talk about investment, economic outcome, we always think about, okay, if it's cost short-term, and we can get back also return short-term, or it's kind of a short-term, long-term. So there's some mismatching maybe in terms of the cost and benefit. So I would like to maybe ask Markus, how about your thoughts from these aspects?
Thank you very much. Yeah, this of course is most important. And here I'm lucky to come from the Max Planck Society because I have the advice of economists. We are trying in Potsdam, you don't know, this is my hometown. We have the biggest institute for the economic consequences of climate research. They're my neighbors even, yeah. So we are in heavy dialogue. So we know about the importance. The price tag to save the whole planet with this technology without return is 150 billion euro, which is nothing. This is about a fifth of the money Germany spends for cars, yeah. You have to pay around, and this is mostly indeed energy. We have to heat up biomass, we have to cool it. So the price for energy is only your ability to move heat from one side to the other. So it's not only heating and cooling with waste, of course, you have to use heat exchange. And even in what we call simple conditions, not over-engineered conditions, we then come up to a price of 20 cents per kilogram or 200 euro per ton. This is the current price tag, and you've seen we built even a pilot plant to fix the numbers, because indeed you cannot pretend to be sustainable without these numbers. This is the point. So we indeed have to make an analysis, sustainability analysis. The revenue for the farmer in saving in fertilizer, and this is at the moment remarkably good because of the Ukraine crisis, fertilizer prices have exploded, yeah, is about 400 euro per hectare. So already the saving, yeah, in fertilizer to get the same yield is compensating for the system, yeah. If you talk about dynamics, farming people are conservative, it's slow, and if they're not urgent matter, like in China, they will not change. This is very clear. But everyone likes money, and what economists can do is indeed give a price tag for CO2, which is currently around 60 euro per ton of CO2. And be aware that 1 ton of carbon is 3.3 tons of CO2. So which means with 1 ton of carbon, we can, in principle, harvest carbon credits of the order of 200 euro. And again, it's so to say, we are already, so to say, zero. If we would, this is the carbon we can prove. If we could indeed make money out of the 70 tons of microbes grown in extra, yeah, you see we have to sell carbon certificates lower, and it would be carbon counterproductive because people would get more money from carbon farming than they would get from food farming. So I just want to say these numbers. I think it's mostly, as I said, an economic and political structure, and to set, so to say, a number of rules, like for instance, CO2 certificates, yeah, allowing indeed such technologies to grow. And for instance, if we would do it in Africa, where there's a lot of sun, where indeed land is largely used up in large parts of the countries, yeah, we could compensate our German CO2 overproduction by making a deal with farmers in Kenya. Yeah, and this, of course, is the most sustainable thing, because it would create a flux of money, which is based on their work, so makes proud. Yeah, and it would serve two problems at the same time. In Germany, we don't have enough farmland to cure our own. We are so densely populated, not as Singapore, but all these countries with over high industrial population, they rely on friends with agriculture. So I hope indeed that these global schemes can be established, but this is most complex. And this is the reason why the world will be not saved in 2035, but maybe in 2050.
Thank you so much. Actually, really, your answer is very inspiring. Actually, you open my mind for another business model instead of...
Yes, it's a business model. It must be a business model. You only save the world if people can earn money with it. It's so easy. If you have to... Yes, of course.
It's a completely new business model. It's a carbon, how to say, certificate, and plus, if you're saving the CO2 emission, actually you contribute also to our planet. So what you just explained actually is related to also my another thoughts about the policy. It's such a big plan. If we need to have this kind of global policy, of course, economic motivation, as you just explained, it seems from what you described, the numbers, it's really feasible, because in both of the amount and also about the timing, the investment horizon, it's really matching. However, we need to some extent always some political influence. But if you can, we can establish this type of global quota. It will create another types of, how to say, the new business model in order to save our planet from this type of scientific carbon neutralization business model.
I repeat, I started with saving the planet by giving up habits like mobile phoning, crusade ships, and this will never happen. I ended with saving the planet by creating extra business, extra farming perspectives, and this might happen. The reason why I chose your forum, iCANX, for it is the multiplier. Yeah, most important, the real weapon of a scientist is education and infecting other people. And we know that the most infectious idea, infectious thing is a thought. So once the thought is in your brain, you cannot stop it anymore. Yeah, and this I think is what we do, what you do with iCANX, yeah, and what we all should do. Yeah, and again, you don't know me. I could have talked about many things where I got big prizes. I decided for this topic because I consider it as my most important work.
Okay, that's really amazing. I can say why I was attracted by iCANX, because I wanted to create economic outcome based on the real scientific, the real high tech. There's so many amazing, how to say, successful business model is due to the success of business model.
I know. This is why, of course, business is extremely important. It's the connection to society.
Business is important, but I should say it's building on the really scientific. That's where make our planet and our life, our society have real impacts.
I agree. You see, in panel we have two characters.
I sound like a politician. I'm not really voting for any kind of campaign. But
okay, it's okay. I should not talk anymore. I give back, of course.
Marty, please. Yeah.
Markus, during your discussion on the business side of things, actually something has come up. Maybe next time you give these talks, you should think about it and mention it. The idea that you can take carbon credits from developing nations that don't have a lot of farmland and have them accounted for or given those paid out to farmers who are growing food in developing countries. What also you're doing is not just saving the planet, but also you're creating peace, because there's no way people can fight when they're helping each other. If you can build that partnership between, for example, Germany and Africa, maybe Kenya, Uganda, or other place like that, then that link between the two countries ensures that there's mutual, cordial relationship, and there's a lot of peace, and there's a lot of other things will follow. Because, for example,
I agree absolutely that eye-height relationship is only possible when both sides are proud and can give something to the partnership. This, I think, is very, very human. We starting as the Max Planck Society, you know, we are traveling a lot. We are taking airplanes and we are doing free carbon credits, but we don't give to a bank. We currently use, so to say, our compensation money to also Africa to subsidize projects which have a certain carbon impact. And it's the self-declaration of the Max Planck Society to support so many projects as we produce CO2 by scientific traveling, which is a lot. So yeah, I want to say this is currently starting, and here indeed my social scientists and my social scientists are absolutely excited because for the first time they can really help us to arrange something because they have got a new tool. Yeah, and I like that very much. But I will consider even more, yeah, because this is the way, yeah, to make a better planet. It's not only about CO2. Yeah, in the very end, we have to go to new business structures.
Very good. Yeah.
Okay, super. Yeah, thanks for all this kind of words for iCANX. I think this time we really got something, meaningful for this, iCANX. The next step, we can get technology and economy and also the society, the social event going together, to be integrated to get something new. Like, Markus say that, inspiring the brain. Once you have the idea, that couldn't stop, right? Yeah. So from my side, I have to say that, really thankful you mentioned about China. Yeah, good things or bad things, especially the young lady, the young professors in Harbin. Yeah, now it's doing great things. I'm proud of that because that's my husband's hometown. Yeah, they have plenty of black soils, the black land. We're really proud of that. We see this kind of scientific, research on the soils was coming out. We're so proud of that. So Professor Markus, maybe I have a question is related with your talks. You mentioned that 1 second, 1 kilo, right? Yeah, can be produced. Yeah. So, I mean, how much about that? Can it, mass production can be supplied to, some, other place?
So the point is you are now using, I think, something which we have to leave. Biomass is not very valuable and has to be carried around. So turning biomass into a soil additive is an inherently decentralized business. Yeah, you don't want to bring it 10,000 kilometers. You will want to collect maybe on the typical size of a township, 10K
That's like a
to the
process,
machine,
right?
Yeah, and the 10K back. And then indeed a farmer can drive to the social factories. It's like a social club and bring his stuff. And after 2 hours, he can drive back with the fertilizer. And this is exactly such a machine. This machine I showed you is good for 20 square kilometer. And it's of the size of a truck garage. So this is something, and we can, if we can bring down the costs for that, and we are not there because we need really Chinese production technology, which are much better than German high-end engineering. If you bring down the cost of such machine to 60 to 100,000 euro, it will go immediately. So it's again this question, transport logistics, how many machines. If you have that, every little township would have such a machine, and then you need 150,000 machines to cure the planet, because you multiply the two numbers and you find out, that this is again what you need to compensate for the 3.2 ppm at the moment.
Okay, I see. I got the point. Yeah, it's like if you got a mass, a millions of users, right? Yeah. Okay, cool. Yeah. So my next question is about you mentioned about this. The one slide give me a big thinking as you mentioned that the soils was the land was the most largest the energy storage, right?
It is.
Yeah, it is. So you are super research within the energy story. I also, working on for the energy, harvesting. I think can you, give some perspective in this, direction? Is that possible to use this?
We did created lignin batteries. Many plants. You really should go as an energy scientist or biologist and drink a glass of tea with them. Yeah, and they call it differently. But for instance, bamboo is, to my understanding, the biggest battery on Earth. So in the winter time, the battery is in a loaded state, because if bamboo pulls back, it puts all the proton-electron pairs, which is the electricity storage of nature, into the rhizome, into the root. Yeah. In spring, yeah, bamboo grows partly 2 meters a day. And don't think that this is photosynthesis. It deloads the root battery to shoot practically up. So every plant has a phase where it does not live from light, but from stored electricity. And I call it now electricity because it's our language. It's a proton-electron pair. So it's not a lithium battery, it's a proton battery. Yeah, but the principle is exactly the same. And to make indeed bamboo grow in spring like that, it has to take from its battery, from its root. And I can even tell you the molecules doing that and how they look at loaded and deloaded. Yeah, because of course, yeah. But now think the other way around. If you want to make very cheap batteries, why not using bamboo batteries? And we are back, sorry, Minue, it's back to economy, yeah. The lithium battery is simply too expensive and it's not sustainable. Yeah, it's 150 euro per kilowatt hour.
I'm so excited. Sorry, I just interrupted you. I'm so excited for this idea of this bamboo energy. So sorry, Alice, I just
it's the simple things. And here with Martin,
I live in Switzerland.
Why can bamboo grow so fast?
Exactly.
Yeah? And it's indeed. And indeed, it's a proton-electron taken from the root system.
Okay, I see. Yeah. So,
a bamboo battery, just to finalize the sentence, would be 10 euro per kilogram.
Yeah, less than that. Yeah, less than
and
that.
then, of course, it's maybe not good for cars. Yeah,
we should have another times talk for this bamboo battery. It's amazing because now I live in Switzerland, but 20 years ago I live in Zhejiang province.
Yeah.
So that make the feeling of for bamboo. I eat bamboo all the seasons. So the spring, as you just described, I need to really cut the bamboo. Otherwise, they will just grow like out of control. I even want to plant some bamboo in Switzerland, but I just worry about my neighbor. Maybe you stop me because I cannot control their growth.
I tell you that, Professor Markus, I will go back to do some experiments because my yard was full of bamboo. Yeah, I have a bamboo yard. Yeah, I'm serious that every year I'm worried about the bamboo booming.
but actually, Markus, I'm glad you brought up the bamboo because there's a time I was looking at the growth rate of the bamboo as a way to understand pumping water. If the bamboo if you watch the bamboo shoots come out, they draw so much water from the soil. And if you calculate how much volume they're moving up, and you start calculating what kind of a pump you need to do that, it doesn't make any sense. When we want to move water uphill, we have to build this very expensive, energy inefficient pump. And there is a tree. I was just watching YouTube videos of the bamboos growing, and I wanted to know how is it moving the water so fast?
With that nanotube inside. Yeah,
it's something like that. This is half explored. It's an exciting topic. It's called superfluidity. So water is pumped practically frictionless in bamboo because it's indeed in nanotubes. You know that the viscosity of liquids in very thin tubes is much lower than ordinary bulk viscosity. Yeah, and nature is playing these tricks all in a perfect way. So Martin, thanks again for this point. This is called, of course, biomimetic materials. We sit there, we learn, yeah, and we don't have to come up with too many own ideas. Nature is so brilliant in many solutions. We only have to apply it technologically. Yeah.
Yes, exactly. Yeah. So yeah, we'll go back to, make some experiments, see how many, electrons was, helped for this bamboo, blooming. Yeah. So actually, it is really interesting and inspiring. Yeah. So thank you very much. Yeah.
It's a
I'm
pleasure. I
thinking,
thank you.
yeah. Let me share my screen again here. So yeah. So thank you, Professor Markus. Yeah, this wonderful discussion and wonderful talk. I think, first I deliver this electrical version, as a certification to you. We're proud that you today talk, yeah, it's not soil, can soil materials make us carbon neutral. We also can do a lot of things. Thank you so much. Yeah. So today we also have another thing as we're going to announce for the iCANX Summit Davos next year. So let's go to this part. Okay, let me share another slides. Okay, yeah. So okay, good. Let me share my slides. Okay, next year we're going to have something new, and we're going to have more fun for this. Because iCANX till now is about 3 years. Next year will be the 4th years. So since carbon 19, we save a lot of carbon. We got this tax online, and people, of course, they want to make more kind of, collaborations and communications on site. So next year, for everywhere and everyone can move freely. So we're going to have this iCANX summit and Davos next July 11 to 12. So, and Davos, Switzerland. So today is our great pleasure. We got this, people here to announce this, iCANX summit the next year. So for iCANX Summit, also, sorry, what's wrong with this? Oh, okay. A different one, sorry. Okay, let me stop sharing this one, share another one. So I open too many windows, okay. Okay, got to this one. So next year we're going to have this summit and the beautiful place. I think everyone knows this. Davos every year they have a super economic summit. So next year we're going to have a new one as a science summit to iCANX. So iCANX Davos Summit 2024 will be the first time for iCANX people to go together. We will invite the world leading figures to share the achievement leaders in the innovation, science, technology, investment, management, and environment together. We also will be highlighted with a few iCANX awards, innovation awards, young scientist awards, and high tech startup awards in these areas. So next year, the theme of iCANX Summit is time. Innovation, science, technology, investment, management, and environment. I think today's talk really covered all this because we have innovations, in science and technology. We also talk about the new business models for the future, how to saving our world, how to develop the futures for the environment to, sustainable. Yeah, so next year on the Davos Summit, we will cover all these topics. Yeah, we will invite the world leading science and the other figures to join this big summit for this. So our organizer team is our iCANX teams, the moderator teams. Have me and Paul and Fulan, Martin, Chris, Minso, Paul, and Mingyue here. So all these teams cover the whole world from different part of the continental. So we'll jump in for this big event. So will be our key organizer teams. And we have confirmed a few plenary speakers. Professor Jean-Marie Lin was from France. He's a Nobel laureate from chemistry. And Professor Jagdish was the president of Australian Academy. He's also our moderator, at the very beginning for iCANX. We're proud of that. We have Professor Saif Rahman was president of IEEE. And we have John Rogers is our first speaker on iCANX. We have Peter Seiss was the co-president of Swiss Academy of Engineering. And we have Chad McKean from Northwestern is also the super speakers on iCANX. We have another Dubius is from Switzerland again. We have Andrew is a UCLA professor, a BRIN project in US. We have Rui Ping Xiao was a super scientist in Peking University. We have Zhonglin Wang is a super scientist in nanotechnology. So this is a few, plenary speakers we confirmed till now. Of course, we're going to have more. Like today, we have Professor Markus. Yeah, he's to talk about this, but you don't know that he also play, funk, rock and roll. So it have a scientific bond. So that's you will met another way, right? Not only talk about science, also plays the best music. Yeah. So we're going to have all this fun for science and for technology, also for a lot of new things come out. And this also will be the first time for iCANX family to go together. Yeah, so all these speakers from different part of the world, we're proud of that. Now we have more than 80 countries, the speakers. We have almost 1,000 speakers, from 82 countries. So yeah, we're going to have all of them to go together. Yeah, of course, welcome more friends, to support iCANX. And we're going to have a few words. Hi, Martin. Yeah, it's your time to introduce our words.
Okay, thank you very much, Alice. For the awards, we will start off with the iCANX Young Scientist Awards. These we have awarded in the last few years, and I'm going to be talking a little bit about that. We also have the Innovation Awards and others, and the Startup Awards, but I'm going to focus on the iCANX. Next slide, please. In the Young Scientist Award, we are inviting people who obtained their PhDs from 2013. Send us one PDF application. And we want you to give us a CV, include a photo and a website with the details about your work. Give us a brief synopsis, about 600 words of your scientific contribution. Give us an outlook and research plan, kind of point to us why you are a rising star, because these awards are actually highlighting that. And they are supported from different sources, including journals who would like to see you emerge as a leader in the field. We want maximum 5 representative publications or patents, and then give us contacts of 2 recommenders. And we highly recommend that as soon as you submit your application, or even before that, talk to your recommender so that they have their recommendation letter sent by January 31st, 2024. Next slide, darling. So to give you an outline of how this happens is similar to how we've done this before. We will first screen out the candidates. We'll have a Young Scientist Award Committee. And this committee will go through all the applications, and then we will arrange for short online presentations, just basically giving us a short brief of your work. And this is going to happen during the iCANX on March 1st. And then on the second, we have the finalists coming together for presentation and Q&A in April 2024. Then we have the finalists will all meet in Davos during the iCANX Summit. And then on the second day, when we have a big celebration, we will award the iCANX winners there. So please send your application, and we look forward to having you there.
Okay, great. So Mingyue, could you please introduce the schedules of the event?
Okay, so since so this is just like a preliminary version. So basically, we will start July 11th with the open ceremony, but we also will integrate also the I should say the panel sessions for several keynote speakers. And then from afternoon, we start the panel sessions and also the like Martin just introduced some young scientists award. So we will also have a big, we say now it's gala dinner, but it's, I should say, it's just like we meet together and eat together the first evening in July, the July 11th evening. And the second day, we will continue the panel sessions based on the different 6 themes Alice just introduced. So basically, we have 6 themes and 6 different types of panel sessions. And also in this process, we will start the case show for the Innovation Award and also Startup Awards. So I think I really also like very much to call the companies who would like to join the events by exhibition. So as you know, Davos has very advanced infrastructure for worldwide really conference. So we have a lot of very nice space for exhibition. So this is also part of my duty to call our sponsorship and also the exhibitors. And finally, most exciting is the evening of 20 July for the award ceremony.
Yeah, we'll have a banquet. We'll have the music show.
Yeah, and with some secret for the moment. I don't want to give you some show players.
Okay, great. Yeah. So yeah, how about the venue?
Yeah, the venue, I think, no, as maybe it's not very well, but on the right side, you can see Davos, actually, it's between Switzerland and Italy. But if you look at the international connection, so from Zurich, from Geneva, and also even from the Basel, you can have also from the Italy side, you have the flight connection. And also, of course, due to the ESG concern, we highly recommend you just arrive the main airport in Europe, and it's very well connected also by train. So that's why I think Davos is also very ESG friendly place for such kind of global conference. We really take into account because Switzerland is the heart of Europe, so it's very well connected to all the main airport in Europe. And also for the hotel or the infrastructure, we will also put online step by step by the information. Actually, we try to establish also our conference partners with the local suppliers. So we'll keep you posted from our website.
Yeah. So this is a big news from Mingyue, right? For the association.
Yes. So finally, I say finally, because it takes actually really more than 3 months to create this iCANX association. Based on my experience, it's recently it's a country actually, I should say, relatively very friendly for the startups and also a lot of different types of legal entities. So it's headquartered by many international organizations. However, because iCANX is it's really a cross-country, cross-border, interdisciplinary, and also recently, again, the Swiss control very strictly all this type of international relationships. So we finally registered officially iCANX in Switzerland. So the headquarters here, I noted in Lausanne, because actually it's in a place more beautiful than Lausanne. It's in Saint-Sulpice. So if you're familiar with Swiss French area, Saint-Sulpice is a very prestigious small village, but it's just like 5-10 minutes away from the 2 Lausanne-based public University of Lausanne and EPFL. So we also call it a village of professors. You will find a lot of professors in this village. So this is our headquarters. And this is our main, what we explained in our registration. We try to keep no-profit permanent organization, which bring together different kind of stakeholders, including scholars, professors, researchers, and also industry leaders. Of course, we cannot reject investors and also the managers, entrepreneurs. So this is actually our, I should say, the population in our future iCANX association. Yes.
Okay, great. Yeah, thanks for Mingyue. This was really great news, for all the iCANX family members. Eventually, we have a family, we have some place to go, some, a long-term, plan can be planned. So welcome everyone, to join this iCANX summit next year in Davos. So this will be our first time to go together. Also celebrate our new, associations, celebrate a new step, for the science and technology and all the social event can go together. We set up a new format next year. So iCANX is connect the future and the universe. I'm sure we can make it. Yeah. So welcome everyone. And also iCANX will continue next week. Yeah, next Friday we have a Professor Damon Thompson is going to talk about the bioinspiring materials. So how to practice the modeling, all of this is a super story again. Yeah. So welcome everyone to stay with iCANX. It's all of today. So yeah. Okay. Thank you very much, and see you next week. Okay.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。像我一样飞越最高山岗。 中。